Okay, not the majority of the audience, so I can get away with saying anything I want. How many of you, out of the people who know what an AST is, has had a formal compiler course done in university? Okay, great. So my talk is a great domain today. Great. Before starting the talk, how many of you can recognize the faces on this slide? Just because the talks, let me make it a little interactive. Just shout out if you know the first photo. Alan Turing, that's correct. Second, Von Neumann. Third, oh, that's Kurt Gödel. Fourth, Charles Babbage. Fifth, Ada Lovelace. That you got to know. Knuth. Dijkstra, that's correct. Dennis Ritchie. This one's good. That's Konrad Zuse. Brian Kernighan, almost there. And the last two are Alfred Aho and Jeffrey Ullman, the authors of something called the Dragon Book of compilers. Great, so let's get started. I don't know about you guys, but back in my days, people, the way you get introduced to computer science is, oh, computers understand only 0, 1, 0, 1, 0, 1. Okay, open Borland Turbo C++, start hash include IO stream, int main, char star argv, int argc, right? Where is 0, 1, 0, 1, 0, 1 there? So that was the first confusion that got me into exploring what a compiler is, how the compilation actually happens, and what are the different steps involved in the compilation process. And it's really a sort of a magnificent magic that's happening in the compiler. So let's take a look at demystifying what a compiler is and how the compilation process actually works. So very simple, right? So a compiler is just basically a big meta program. Do you guys know what a meta program is? Shout, just shout. Okay, a meta program is a program that treats source code as its data. So it's a program that treats another program as its data. It's a meta program. It's very simple, right? So what a general program is, a program that takes some data structure, x is equal to 0, y is equal to 0, whatever, manipulates on that, and generates some kind of an output. A meta program is a program that takes source code itself as its data. Let's say a Python file, let's say a C file, let's say a Java file. And it's just another big software which has a front end, middle end, and a back end. Don't worry about what these are. We'll look into them. And unless you're doing a compiler course, not much of it is, not much detail is necessary anyway. And between these front end, middle end, and back end, there's something called the intermediate representation, in which we're going to be playing a key part today. AST is one of the intermediate representations between these front end, middle end, back end. So front end accepts C, Java, any modern programming language, and the back end generates ARM, x86, PowerPC. So how many of you are comfortable with these terms? ARM, x86, PowerPC, MIPS. Great. Anyone can shout any other platform? ARM. Great. So one favorite platform of mine is the IBM Cell processor, which anyone knows what the IBM Cell processor is significant for? Exactly, it's the architecture chip of the PlayStation 3. So I have a PlayStation 3 at home. And so the final code that runs on each platform, it's really a fascinating read. You've got to look at this Intel's developer manual. Just Google it. You'll get it online. Take a look at the various different types of assembly instructions that are supported by each platform. So I think my voice, okay, now it's fine. So ideally, at the end of the day, these are the things that gets executed on a particular platform, right? So this is the final output. So coming back to the front end, middle end, and back end. So we saw what an instruction looks like. It's the final and, or, not, bitwise add, etc., and so on. So if you want to go one step further, these are implemented by logic gates, usually NAND gate, NOR gate, AND gate at the chip level. But let's not go into that. Coming back to the front end, middle end, back end. So front end is usually, it has a few things. It's called lexing, something called parsing, something called semantic analysis. The middle end is usually, don't get overwhelmed by these terms. you'll understand everything. So lexing, parsing, semantic analysis, middle end has optimizations, more optimizations, and the back end, of course, ideally generates the target platform's instruction set. And this is, of course, a heavily simplified version of a compiler. So this book is a favorite book of mine. I had this for university as well, and a great teacher too to go along with it. I think there are copies available of it on Amazon. You just, it's kind of cheap. It's a very fascinating read. You got to read it. If you take a compiler course or not, you just have a read at it. It's a really enlightening book. Right. Grammars, right? So a lot of letters here. Do not get overwhelmed again. We'll do a quick exercise what this grammar is. Like all human spoken languages, right? So computer also have grammars. So the English language has a grammar. The Hindi language has a grammar. All languages has a grammar. And these languages sort of adhere to a grammar. So you can't use English words in Hindi. You can't use Hindi words in English, and so on. And there are different types of grammars. For example, so I don't speak Hindi at home. So I'm from Bangalore. I'm a Kannadiga. So the biggest confusion for me in Hindi is genders. Right? So I always get confused with genders because in all the other languages, the gender is associated with the subject in the subject-object verb. He went to the store. So he is the subject. But in Hindi, it's the other way around. You give gender to the object, and it's always confusing to me. So I mix up all the genders around. So grammars, right? So every language has its own grammar. And we need a formal representation of each grammar. So this, for example, here, let's say this is a grammar. And let's say we have a string called AAAB, right? It's a string, AAAB. It is a word, it's a phrase, it can be anything, it's just a string, right? So does this string AAAB belong to this particular grammar or not? Let's analyze. Now I'm going to formally define a grammar, so I'm going to use some notation to define this grammar. So mathematics, symbols, etc. are the best types of denoting ideas, right? So this is just some notation. So I'm telling S gives AB, A gives the letter A and the capital A and something called epsilon. Epsilon is just a null string. And I say B gives B, small b, or BB. So this is my grammar set. And now I want to see if AAAB belongs to this grammar or not. So I'm going to do some things here. So initially I'm going to say, start with I'm going to pass AAAB with this grammar. I'll say S, I'll take S. Now we know that S gives AB, right? Agree with me? So we know that S gives AB, so I do S gives AB here. And we know that A gives AA, so I do AA. From AB, I replace this A, this particular A here, with AA, because I know that A gives AA. And then again, I'm going to take the next A here. Again, I'm going to replace the same thing recursively. So I'm going to say that this A gives AA. And then I'm going to do this A gives epsilon, right? Because I know that A gives epsilon. So epsilon is a null string, so I'm going to just ignore that. And then there's final B, right? And I know that B gives B. So there you go. I have passed AAAB. Right? How many of you have understood this? Fantastic. Fantastic. So now you've just understood something called as top-down parsing. Also, in this particular case, something called as the LL1 of grammar. Now, LL1 of grammar means left to right scan and leftmost derivation. So if I go back to this previous slide, did you notice that we scanned the thing from left to right? We did left to right, right? Substitution. And we did a leftmost derivation for one string here. One string here, one string here, and one string here. So this type of parsing a particular string is called LL1 grammar. For those of you who are just coming in, you missed out something cool. Great, that's LL1 of grammar. One is for one substitution. One stands for one substitution. There are other types of grammars. There's LR, there are a lot of grammars. And This particular grammar is a context-free grammar, and what that is I will not go into. Do go through the compiler's Dragon book. It's quite fascinating again. Okay, what does Python's grammar actually look like? Let's have a look at it. Have any of you seen the Python's source code? Oh, quite a few people. Okay. Okay, to you people who've seen the Python source code, I have a question for you. Do you think Python is compiled or interpreted? Shout. No interpreted? Some both? Actually, both is the right answer. So it's neither compiled nor interpreted. And I think the question, is Python compiled or interpreted, itself is wrong. It's the implementation that is compilation or interpretation. You can do whatever you want with any language. You can interpret C if you want to. You'll have grammar, you parse it, you interpret line by line, you do whatever you want. So a language is never compiled or interpreted. It's the compiler or the interpreter that you write for a particular language. Right? So let's take a look at the Python grammar. I'm going to open up. Can you see this? Ah, perfect. Oh, wait. I think I've got the wrong tab open. Ah. Everybody see this font? Yes? Great. So I've downloaded Python 3.5.2 here in my system, and these are the various folders that's there in the Python source code. Now let's take a look at Python's grammar file. So it's in the grammar folder, and the file is called just grammar. I'm going to open it with my current favorite text editor, Sublime Text. Okay, it's not coming up here in the extended screen. There, and just go open it with Vim, which is also one of my favorite editors. Oops, I'm in. Great. So this is the grammar for Python. Just take a look at it. Now we saw how a grammar looks like. S gives A, B, A gives AA, blah, blah, blah. So this is a rough grammar. So ideally here's where you'll want to start. Statement, STMT, colon, simple statement or compound statements. Remember, S gives A gives AA or epsilon. It's just the same way of representing. Statement gives simple statement or compound statement. And within simple statement, you have further substitution rules. And this is the grammar for Python. It's just a 150-line file. It's another fascinating read. Just go through it whenever you get the time. And the complete Python language is in a 150-line grammar file. And this grammar is parsed. It's lexed. It's parsed. It's built into an AST, and etc. Let's see how that's done. So design of the CPython compiler, and there's a PEP for this. It's PEP 339, and it has a really, really fascinating explanation of how it works. So essentially, it starts with a .py file, whatever you write, x is equal to a, x is equal to b. Then the parser pgen.c is a file in the Python source code. So hopefully you know by now Python's written in C. So there's a pgen.c which generates a parse tree in between. The parse tree is an input to something called as the AST.c, which generates the abstract syntax tree, which is what we'll be looking at today, which is an input for compile.c, which generates something called the control flow graph, which is an input for compile.c again, which generates the bytecode. This is the rough design of the CPython compiler. So it's 4 steps, quite simple, takes a py file, does things, generates parse tree in between, AST in between, CFG in between, emits bytecode. What is bytecode really? Let's take a look at bytecode. So there's something called as the DIS. How many of you are aware of DIS, DIS? Okay, I can still show it. So I'm going to open up a Python shell, and let's say I'm going to define a function def foo that's going to return a plus right. So this is a function. It's a normal function. Then there's this module called dis, which disassembles the bytecode of a function and gives you the opcode instructions. So basically, this is what is happening. This is the opcode. So it says in this.this load underscore fast, binary add, return value. And keep in mind that this is not platform dependent. This is not x86 or this is not ARM code. This is the bytecode instruction. And this bytecode instruction will further be parsed by it'll further be passed by something called ceval.c in the Python folder in the Python source code. Really, you got to go through the source code again. So that ceval.c is a C file, and you know how C files get executed. There's you either use GCC or CLang or whatever and execute this. Okay. So quick breather until here. This is Calvin and Hobbes because I made. So I think a few people from here noticed me making these slides in between the talk. This is just filler. So I didn't know if I can make it 30 minutes through the talk or not. So just put this up. Last minute panic. That's usually what happens to me. So this entire slides I put it up in my flight from Bombay till here. Which reminds me, I flew in from Bombay. I didn't introduce myself. So I'm Suhas, senior data scientist at craftsvilla.com currently. It's an ethnic store. And previously, I was a data scientist at a startup called Gramina. And before that, I'd worked for VeriSign, which was a DNS services and a public key cryptography company. Currently, I'm doing data science, and it's been good so far. Filler's done. Let's move on. Accessing the abstract syntax tree, coming to the core part of it, very nice part of it. Let me code this actually, right? I don't want to show this in the slides. So I promised the organizers that I'll live code the entire talk. Unfortunately, I couldn't keep up to the promise. It's half slides, half coding. You got to sort of adjust with that. Right, so let's have let's say a simple file. I don't want to do this here. Let me go to backup. This is a good folder to work in. mkdir live, cd live. Let's make a example.py. And is it in insert mode? Yes, I can't see what's there. This thing is obstructing my view, and this is an extend monitor. It's not a mirror. I'm too lazy to figure out how it works in OS X to mirror, so I'm just going to do this. Right. So let's have a simple code. A is equal to 26, B is equal to 0. That's not 0. Print A plus B. By the way, anyone know the significance of 26, the number 26? It could be anything, just random shout. What do you think? Day after tomorrow. Number of alphabets. Yeah, that makes sense. Yeah. I had a different thing in mind though. So 26 is actually the only number that's between a perfect square and a perfect cube. 25 is 5 square, 27 is 3 cube. 26 is the only such number in the entire real number system that's between a perfect square and a perfect cube. Fascinating. So yeah, back to abstract syntax trees. Right. So I'm going to save this file. I'm going to go to Python here. There's this module called AST, which is by default provided in the Python standard library. And you just got to import it and say, let's say my source is equal to, I'm going to read that source file which I wrote. Open ex, what did I name my file? ex.py. ex.py.read right? So I have the source now, which is in some string format. Now I can just parse this, saying tree is equal to AST dot parse of source. Now I have a tree. Now this is the abstract syntax tree, AST dot module object, you can see. Now you can do some interesting things with it. You can just print it out, let's say, or you can walk the tree. It's a tree, basically. So visualize this like this, right? I didn't put a visualization slide, sorry for that. I'm just going to show it with hands. Let's say A is equal to B, simplest of statements. No, sorry, A is equal to 26, right? So just think of the AST as a tree with each of these as nodes, with equal to being the root, A on the left, 26 on the right. You can visualize that, right? So that's an abstract syntax tree. But how did I decide A and 26 got to be the leaf nodes, equal to has to be the root node? How did I decide all that? There are different ways of doing this as well, but Python's AST adheres to something called the Zephyr ASDL syntax, or Zephyr ASDL norm, or whatever the word is. Adjectives are not coming. Cool. So you can actually look it up. Google for Zephyr ASDL. It's a paper. It's an interesting read too. So Python's thing adheres to that format. So now I have the tree module, and coming back to this, so I can walk it, right? So I can say for node in AST.walk of tree 2, 3, 4 print node. Whoa, a lot of objects. So there was a module object, then there's an assign object, then there's another assign object, an expression, a name, a num, a name, a num, so on, so on, so on. And this is a little overwhelming for me. I don't know what's the root, what is the leaf, how the structure is. So there's a library called AST unparse. You can get it on PyPy. Pip install AST unparse, I guess. So I can just do AST unparse. Let me print it off. AST unparse dot dump of tree. Right. So now it's going to give me a little pretty printed version of it. So I'm not going to scroll up or down. You see there's an assign somewhere there, and assigns children are an ID and a target ID and then a value. So assign the equal to, and then so the equal to is represented by the assign object. Now it has children, targets, and value. So this is a little weird again. How do I access each and every single node in the AST? So I can do things. So tree was my node. So tree.module, if you remember, body. I think I'll have to scroll up to make this clear. Right, so module was the root node of the root object of the tree, and the root object has a few attributes like body. So I'll just access tree.body. Tree.body is an assign, so it's a list. It's an assign object, it's another assign object, and then it's an expression object. So that, if you remember what ex.py was, it was a is equal to 26, b is equal to 0, and print a plus b. So that's the body. It's an a is equal to 26 assign, b is equal to 0 assign, and a plus b is the expression. So that's the AST here. So I can also, so that's the initial looking at an AST. Let me get back to my slides here before what was I planning next? Okay, let's have a little fun. I forgot what I wanted to do next, but let's just have a little fun. So instead of reading a file, you can just parse an AST as is. I've already imported AST. Let's say my tree should be AST.parse of, let's say x is equal to 26 again, right? Now this is my tree object again. So I can just give a single expression statement and get its AST. Now I can also sort of try to modify it a little bit, right? So I know that tree.body.AST I hope it is, no, tree.body.0. Any idea why I'm doing body of 0? Because there's only one statement, correct. Tree of body of 0, which is an assign object. And what is in an assign object? I don't know what properties an assign object has. So I can just look it up through ast.dump. An assign object has targets. So I can get the targets and then the name. Name is the ID. A list object has no ID, so I have to go 0.id, which gives me x. Now's the time when you have to laugh with mu prefixed. Muhahaha. This is great stuff. I got a single variable name, right? So now I can do this. Oh, before that, from an abstract syntax tree, I can get the source back with AST unparse. I'll just demo that. AST unparse dot unparse of tree, and I'm going to print that x is equal to 26. I unparsed it from the abstract syntax tree. Now I have the source code back. Okay, back to abstract syntax tree now. Now that I can access a particular element name, what if I do this? Let that sink in. Right? So we just went into the source, runtime, parsed the AST, did some evil stuff. And most of this talk that's going to come up in the next 15 minutes or so will be evil. I'm not going to show you real world examples. You can always look that up. There'll be more talks. But I'm going to do some evil stuff. Right? So now that we know how to do things like this, let's get a little formal. Right, I'm going to have a better file. Let me this is live folder. I was preparing a few examples. Let me look that up. Backup, ls, cd backup, example, sorry, cat backup, example. Okay, so we've done this already. Backup example 2.py. Yes. So now we have a small example. It has a function call def foo return a plus 1729. What's the significance of 1729? The Ramanujan number. I don't have to tell you that. A big fan of number theory, by the way. You should have guessed by now. Foo of phi, it's calling that foo twice, so just adding whatever number we parse it to 1729. Great, what can we do with this? So let's hack this. Let's write a, I know what, I'll just open a new window here, do this, get this on my system. Yes. Just give me 1 minute. CD lab, CD PyCon, CD 2016, CD BK, CD example. 30 more seconds. Oops. 15 seconds. Great. It's coming back here. I did kept my promise. Vim, let's say hack, example hack dot py. It's not pu, py. Right. Okay. So I'm going to import AST again. And now I'm going to define something. I'm going to define a class. Right. I'll say func call visitor, and I'm going to extend this with node visitor. This is just a formal way of visiting each nodes in an AST. Don't get too overwhelmed or confused by the exact semantics and the logistics of it. It's just I'm extending a class And I get a few superpowers if I extend node visitor. So I'll show you what those superpowers are. Where is my cursor? Here. So I'm just going to calculate how much 1, 2, 3, 4 def visit underscore call. So visit underscore call is a specific syntax. So you know that every source, every part of your code has a corresponding AST object, right? So we saw module, we saw body, we saw assign, we saw expression. And a function call has an object call with it. So if I say visit underscore call, it's usually visit underscore xxx of the format. Visit underscore call will visit all call nodes in a particular 4, 1, 2, 3, 4. And I'm just going to say, and it accepts a node as an argument. So I'm just going to dump the node. AST.parse, open, let's say bkp example 2.py.read, and re is equal to func call visitor dot visit of tree. That's it, right? So you know what AST.parse does already. The next thing is I'll take that tree which AST.parse gives me, and I'm going to visit that tree with func call visitor. It's basically what we did, AST.walk, similar but more formal. We'll see why we're doing this in a moment. So this is xhack.py, so I'm going to do python xhack.py. And as expected, it'll give me func name id foo and func name id foo, because we are calling, note that it's only giving the calls and not the function definition. It's not giving foo thrice, but it's giving foo twice. Right? So this is the power of AST. You can just specify which node. But if you want to modify code usually or parse or something, if you use a regex, if you just use foo, it's going to give you three results here. Of course, there are more intelligent regexes you can use, but that's not the point. So I have foo and foo with me here. Now that I know how to do this formally, vim xhack.py, I'm going to open that again. And no, let me just show you, instead of typing and wasting time, let me just show you the example that I've created already. Backup example. So instead of vim, I'll just say cat, right? So what this code is doing, it's just importing AST unpass. I have a class called evil modifier, which has evil intentions. So what I'm doing in evil modifier is I'm visiting a call, all the call nodes, and that node, I'm going to throw away that node. In that place, I'm going to return something else of my own. Okay. So what am I returning? I'm returning a call itself. So for that call, I can return assigns as well. Foo of phi, I can change that particular foo of phi into a is equal to 2 as well. But that sort of beats the purpose. I have something more evil in mind. So I want to change foo of phi to evil underscore foo of phi. Right? I want to plug into source code, see where all instances in that source code the function foo is being called. And I'm going to change that to evil foo. Okay? That's what this code is doing. Now, so I'll just look at what was my right? So this was my code, foo of phi and foo of phi. And now if I run it's that simple. So just got to extend AST.node transformer, plug in your, to whichever call function, just plug in your particular node. You know how to make a node. Just return it in place. So instead of calling foo, now in the function, I'm calling evil foo. And there are a few uh, uh, undiscussable things that you can do with this. Like let's say that someone is using the requests library, let's just say. And let's just say they're making a call to a particular web service. Yeah. Yeah, that's about it, really. Great. So, what's the time? It's 4:36. I have 10 minutes left. I'm doing good. That's about ASTs, really. So there are more things that you can do with it. There are a lot more actual real-world use cases. We saw a really, really great example in the lightning talk today, the go-to. There are domain-specific languages you can build with it. In fact, Ruby on Rails does this extensively with its database models. So you can actually convert the entire SQL into a Python code like he showed in the lightning talk today. A lot of possibilities, hacking into the code itself, modifying it in the abstract syntax tree level before it gets emitted to the bytecode. It's a lot of fun. So before we end the talk, let's look at something called Flake 8. We can actually write a plugin for Flake 8. How many of you have heard of Flake 8? Everyone, not bad. So what I'll do is I'll just show it to you instead of actually coding it. Okay, so this is the premise, right, of my Flake 8 plugin. Let's just say I'm an evil manager. So I'm using the word evil a lot today. Sorry. I did this thing in the last PyCon talk too. I gave a talk in 2015 edition of PyCon about metaprogramming. We used the word cool around 100 times, and this time it's been evil. Personal quest of mine to use one word repetitively. Okay, great. So the premise, coming back to the premise, let's say I have let's say I'm a project manager, and I have a very obsessive constraints about your code. I want to ensure that all of your variables start with meow. Okay? Or it will fail the continuous integration and you'll be sent home, things will break, whatever. So I have a example here, cat, or cat backup meow. Right? So I have an example here, example.py. I'm just naming meow equal to meow and printing meow. So how do I run Flake 8 on this? Okay, so we can actually write a Flake 8 plugin. I'll show you how that looks. So this is actually how the structure of a Flake 8 plugin looks like. You can have your own. So ideally, you'll start with a setup.py function, setup.py file. It's a series of lines which tells the Python setup environment of where the entry points are, how do I treat the installation, and so on. How many of you actually published a Python module onto PyPy? That is amazing, right? So setup.py helps you formalize these processes, make your Python a package. So that's that. And okay, so I have this flake8 meow.py where I have a class called check meow, name and version, blah, blah, blah. Let's come to the, let me reduce the, no, you can't see, right? Okay. So this is the function which comes in first for a Flake8 plugin. You're going to start with def run. This is a standard that Flake8, so this is a Flake8 plugin, by the way. You can define your own plugins. So you start with run, and so you have this tree that gets passed on while you're initializing the object of, while Flake8 itself is initializing the object of check meow. So in the init, it actually sends you the tree and the file name for it, right? And So you get the tree, obviously you know how to walk. So you just define the run, you have the tree with you, that's it, the playground is yours. So this is an example. So what I'm doing is then if is instance node and ast.name, so all instances of name, that is variable name or whatever, I'm checking, I'm calling the function check meow. And check meow just returns node.id if node.id equal to meow, else none. This is just a normal ternary if else. So if there is meow, I'm going to yield that error. So if I find a meow, I'm going to yield that error. Yield that error. So which line number, what the call offset is, and what the error message is. So I will install this plugin. So the way you install is pip install e dot, I think I'll install it. I've already installed it. So now that I've installed my flickit plugin, I'm going to go and check that on flickit xhack, right? Ideally, this should show nothing. And it should show some other flickit errors, but not for meow. Okay, it says in xhack, this is a E302 from flickit. It says expected 2 blank lines, found 1, whatever. But the real fun is when I run this on, what was my meow hum? There you go. That's the flickit error. Found a meow, please do not meow at meow. That's about it. The at meow tells where it actually found it. 1:1 tells you the line number and call offset, and you can give whatever error message you want. And this is a static check. You can go literally mad with the things that you can do. Some of the things I did at my previous company, Gramner, was check for excessive usages of the stir function, because Unicode, don't use stir. You can actually go and modify. So this was just checking for meow, but you can actually modify meow into other things. You know how to modify an abstract syntax tree. You know how to control that now. You're all empowered. That's the example flickit plugin. It's 443. So we did absolutely silly things with node visitor and node transformer. And we did even more silly things with flickit. You can, again, if you haven't followed me yet, that's my Twitter, @JARGNAR. That's my GitHub, JARGNAR. It has nothing to do with the word English, word jargon. And that's about it. So hacking is a mindset. It's not a skill. Thank you. Yep, questions if you have. Yes, sir.
Can you always get the same exact code back by uncompiling this tree? Or
Sorry, I didn't get you.
Like if you take some code and you generate the AST from it and then you uncompile it.
Yes, you do.
You always?
Yeah.
Okay.
So his question was, I changed foo to evil foo. Can I add more arbitrary functions? Yes, absolutely you can. So just shout it out, I'll repeat the question. Very, very subjective. It depends on your situation, really. If you want to be doing that a lot, then don't do it. Use probably Erlang for that. If you want to keep hot loading stuff, Python is not the language for you. AST is it's more of a one-time thing or a two-time thing at most. Exactly, exactly. Yeah. Thank you,
So,
sir.
just want to ask if anyone wants to jump into AST and then learn more, then is there any online site or like videos or like course, anything?
Very honestly, I learn through Google. I just Google things. It's- Not this. Um, so, with respect to AST, at least the standard documentation is not so exhaustive. So, there's this thing called green tree snakes, which you can look up, Python specific. Otherwise, do read that Dragon book. It's really good. Yeah. Yeah. So a meta class is a class of a class. That's quite about it. So in the Python's ecosystem, at least, let's say you have a class called foo, which we defined. The class of foo is usually type, the root class, right? So it usually comes in handy when you have domain-specific restrictions. Let's say we are implementing a domain-specific language. Let's say we're writing a SQL interface for maybe Redshift, maybe MySQL, maybe SQLite. You can have one meta class which sort of behaves, and you can have multiple classes which are of that type. Note that this is not inheritance, but behavior. So the difference between inheriting and adhering to a particular class, a dog inherits properties from an animal, but we are all living beings, something like that. So when you want to go beyond properties behaviorally, then you use meta classes. And quite a few more use cases for meta classes, especially in Django. It's used extensively um, for various purposes. You can look up Django's documentation. It's a very good source. Yeah, the one in the last. Oh no, I can hear you.
Great talk, by the way.
Thank you, thank you.
But I'm trying to sort of still get an answer. It's a great hobby project, and we've all done disassembling at some level in
Correct.
C or C++.
Correct.
What are larger and real use cases for this kind of a thing is what I'm trying to understand.
The Django example, oh sorry, that was not AST. So abstract syntax trees, usually for PEP8 and flickit, it's completely written with AST. So linting, checking. A real example is code integration, right? So in my previous company, I did not let anyone succeed their code if they had stir calls in their code. So sanity checking, modification, if you want.
But why wouldn't we do it as a static checking before the AST is generated, maybe?
No, it's just convenient to do so. So you don't have to write regexes, so you don't have to write other things, right? So you have the access to a tree. So it's a meta program really.
Yeah.
So your input is the source code itself, and you treat source code as data, as a tree. Right? So it's a very convenient representation of source code. And of course, the biggest use of ASTs is writing a compiler. So we run on compilers today. Our world runs on compilers.
Right. Thanks.
Great. Last.
Yeah, answering to his question, so one example that I've seen where AST is used is there's a program called cscope, which is used to browse C source code of large projects. So somebody has written a pip module called PyCscope. So he has used AST to modify, to go through Python source code of large Python projects and spit out a cscope.out file. So the cscope program can read that file. So that's a PyCscope is a way for programmers to browse through Python source code to find variable names, function names, and jump through it.
Okay.
Yeah, that's.
Okay, I'll not take much of the next speaker's time on to you, sir. Thank you again.